Okay, so we now move on to alkynes, which are triple bonded carbons. And these carbons contain one sigma bond and two pi bonds. And they are termed unsaturated because they also lack the amount of hydrogens, and consequently, the carbons involved in the triple bond are sp hybridized. And so, the alkynes in nomenclature use the suffix "-ine", Y-N-E. And here are some examples: ethyne, but2-ine, and 2,5-dimethyl hex 3-ine. Okay, so how do we name alkynes? Well, they're pretty much named like alkenes, in such that they are determined by first determining the priority functional group. In this case, we have the alkyne. Then identifying the parent chain, or the longest chain containing the alkyne, which is, for example, in this case, we have 6 carbons. One thing to note, please don't confuse that this point where the triple bond ends is not a carbon, because actually it is. It contains a carbon there. And so when we usually draw alkynes, okay, we usually draw it in a linear fashion, because that's how it's shown. That's how it's molecularly structured. It's in a linear form. So this point here where the triple bond ends signifies another carbon. So this is 1, 2, 3, 4, and 5, and 6 carbons. So we have 6 carbon alkyne hexyne. Okay, we determine the substituent. We have an isopropyl group. I'll be using it just to be a bit shorter. So we use the isopropyl group, and then we start numbering. We imagine that the isopropyl is not there, and so we start numbering closest to the alkyne. 1, 2, 3, 4, 5, and 6. Okay, and then we only take a look at that which is necessary. Okay, so isopropyl and then hexyne. Okay, so 1 and 3. Okay, so the name is 3-isopropyl hex 1-ine. We assemble the name by placing the number between the parent name, so hex 1-ine. Okay, in this case, letter Y in nomenclature is actually pronounced like a vowel, so that's why we end our prefix hex with a consonant hex, not hexa, but hex 1-ine. Okay, so 3-isopropyl hex 1-ine, or if you may encounter that it may be written as 3-isopropyl 1-hexyne. Okay. Now if we have alkyne substituents, much like alkenes, we just need to use the suffix -ine-il. Okay, so we do the numbering again. We have 3 carbons. Don't forget that wherever a triple bond ends, there's a carbon. 1, 2, and 3. Okay, so we have 3 carbons here. Prop. Okay, 3 carbons. We have an alkyne. That's why we use the -ine. And then it's a substituent to a parent chain, -il. Okay, so when we form the name, we must attach the number inside. So prop 1 enyl. So alkynes can also have a common naming system, and they use the term acetylene as the suffix. So when writing the name, they use the alkyl group on one side plus the alkyl group on the other plus acetylene. So for example, the most basic form of this is acetylene, which is a flammable gas usually used in forging or pottery, to heat up the clay pots. And then we have methyl acetylene, which is a methyl group connected to the acetylene group. And likewise, we have isopropyl methyl acetylene, which is 4-methyl pentuine in its systematic name. So let's try some exercises. Provide a systematic name based on the structure. Okay, so here we have an alkyne, YNE, and then we connect all the carbons. So I usually draw a dot here so I don't forget that there's a carbon between the end of the triple bond. So 1, 2, 3, 4, and 5. Pent. So that's 5. 1, 2, 3, 4, 5. That's pent. Okay. And then we start numbering at position 1, 2. At position 2, we have our alkyne. So the name of this is pent to ine. Let's see. Okay. So it's pent to ine. Okay. Next, number 2. Let's find each 1, 2, 3. Okay, we have an alkyne there and an alkyne here. We count the number of carbons linking these two together in the longest chain. 1, 2, 3, 4, 5, and 6. So we have a di-ine, meaning we have 2 ines, and then we have a hex. Okay, we have 6 carbons. Since this is a consonant, we have to end the hex with hexa. Okay, we do the we look for the substituent. This is a methyl group, and then we do the numbering as if the methyl group's invisible. We start here, 1, 2, 3. That's where the methyl group is. 4. That's where the triple bond is. 5, and then 6. Okay, so we have hexa 1,4 diine, and at the position 3 we have methyl. So the name is 3-methyl hexa 1,4 diine. Okay, 3-methyl hexa 1,4 diine. Okay, let's look at number 3. Okay, we have a triple bond. Okay, so if I'm not mistaken, the triple bond has a higher priority than alkanes. Okay, much the same as alkenes, and so we must not use the ring. Rather, we will start by identifying the priority functional group, which is this alkyne, and this has in total 2 carbons. Okay, we cannot get this carbon because this carbon is part of the cyclic chain. And so we'll stick with these two carbons. And so we have an alkyne, an S sign. Okay, no numbering needed for the for it's only two carbons. Okay, and we have a substituent. Okay, which is a cyclopentyl. Okay, cyclopentyl ethyne. Okay, so we have cyclopentyl ethyne, but ethynyl cyclopentane is also acceptable as a systematic name. So in either case, both are accepted. But from what I know, I think the preferred one is ethynyl cyclopentane for the 2013 method. Okay, so let's try the next one. We have alkyne again, YNE, and then this is in a ring system that's 8 carbons in size, cycloocta. Oct. Okay, we end in a consonant and then we start with Y, which is treated like a vowel, so cyclooctine. Okay, now let's look at the next one, number 5. 1, 2, 3. So we have 1, 2, and 3 alkynes in a straight chain, so this should be easy. We have 1, 2, 3, 4, 5, and 6. Okay, 6 carbons, so we have a hex. Okay, triene. We have 3 alkynes. We can start the numbering anywhere, it's symmetric. If we start here, 1, 3, 5. Okay, so hex 1, 3, 5 triene. But since we ended with a since we start with a consonant, we have to end with hexa. Okay, hexa 1, 3, 5 triene. Okay, hexa 135 triene. Okay, and for the last one, we have alkyne here, alkyne here, alkyne here. Okay, let's connect them together. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we have 10. We have DEC, dec, diene. So we start with D here, so we have to end with deca diene. And then we have a methyl group here. Okay. So since both are terminal alkynes, terminal meaning they are at the end, we can actually start anywhere. However, in that case, let's consider something else, which is the position of our substituent, the methyl group. And it seems that it's closer to the right hand side. 1, 2, 3, 4, and 5. Okay, if we started here, it would have been 1, 2, 3, 4, 5, 6. We would have gotten a larger number. So 1 and 5. So when we write the name 5 methyl deca, okay, oh, we didn't determine 6, 7, 8, 9, deca 1, 9 diene. Okay, 5-methyl deca 1,9 diene. 5-methyl deca 1,9 diene. Okay. Okay. So now we proceed to enynes, which are compounds which contain both alkenes and alkynes. So how do we name them? Well, what you first want to do is choose the parent chain or determine the parent chain with the most unsaturated bonds. In this case, our simple example, we have no choice but to select the main chain. It's a straight chain after all. Okay, so it contains an alkene and an alkyne, and so what we can do is determine the number of carbons encompassing all these two unsaturation points, alkene and alkyne. So here we go. Since we have 5 carbons, 1, 2, 3, 4, and 5. Okay, we have pent, which means it's 5 carbon. We have an alkene N, and then an alkyne ine. Okay, so N comes before ine when naming. Okay, next we number both the alkenes and alkynes as a set, regardless of priority. So it doesn't matter whether the unsaturation is an alkene or an alkyne. We will treat it as both unsaturation points. So here are 2 directions, and we will choose between the green direction, which gives us 1 and 3, versus 2 and 4. And of course, since the green color direction gives us a lower set of numbers for the substituents, or I mean the alkene and alkyne, then we will choose the green direction. So 1 3 beats 2 4. There we go. So the name of this compound is pent 3N 1-ine. Okay, now here are some complicated situations, but let's simplify this. Okay, so this is with regards to numbering. Okay, so if there is a tie, this first example, this is a first tie example. If there is a tie between both of these directions, the green and the blue direction, we will treat it much like how we treat substituents. So what we do is we look at the whole set and see which number set gives us the lower numbers. So 1 3 6 beats 1 4 6, and so we will choose the green direction. Okay, if there is still a tie, okay, let's look at this next situation. We have 2 different kinds of unsaturation, alkene and alkyne, and each direction gives us the same set of numbers. Okay, so what we do is we prioritize the alkene over the alkyne. So this is in the most extreme cases where there is a tie. The alkene takes precedence over the alkyne. So in this case, we will choose the green direction. So this will be our numbering system for this unsaturated compound. Okay. Okay. So now here are other tie cases, this time with regards to choosing the parent chain. Okay. So when choosing the parent chain, if there is a tie between 2 directions, okay, here's the red direction and here's another direction with blue. Okay, if there is a tie, choose the parent chain that has more carbons. Okay, so you can see that this direction is longer than if it was formed this way. Okay, this still has 2 unsaturation points. This has 2 unsaturation points, and even if we started this way and went on this way, it would be 2 unsaturation points. But this set, this choice of parent chain gives us the most amount of carbons, which is 7 carbons. So this is what we will choose as our parent chain. And here's another tie case. If there is still a tie, okay, then we go back to the rule that if there is an extreme case, okay, of tie cases, we have to choose the alkene over the alkyne. So both of these gives a 6 carbon direction, okay, but we choose the direction that gives us more alkenes than alkynes. So this is for the extreme case. Okay, so let's try these moderate exercises. Okay, so we have here a cycloocta compound. You can see it has 1, 2, 3, 4, 5, 6, 7, 8. Has 8 carbon atoms. So cycloocta. Okay, and we have 2 alkenes. Okay, so we have a diene, and then we have an alkyne. Okay, now we'll do our numbering system. Okay, and if you will confirm this, this is the most efficient, or the number set that gives the lowest set of numbers for the locant numbers. So 1, 2, 3, 4, 5, and 6. So at position 1 and 3, we have the alkyne, and at position, alkene, and at position 6, we have the alkyne. Okay, 1 and 3. Okay, so one last thing that might be missing is, notice that these alkenes are inside a ring. Okay, so every time there's an alkene, try to check if there is a stereochemistry involved. Okay, so in this case, the alkene is in a 8-membered ring, and remember, our stereochemistry applies for rings beyond 7 carbons in size. Okay, so we have 2 alkenes, and if you look at, since they are simple, you can probably guess that the alkenes are in a Z conformation. Okay, so at the positions 1 and 3, there's a stereochemistry Z. There you go. So we have 1Z, 3Z, cycloocta, 1,3, diene, 6, ine. Okay, so 1Z, 3Z, cycloocta, 1,3, diene, 6, ine. Okay, now let's proceed to number 2. Okay, so here we have our first case of drawing given a name. Okay, so what we can do here is we can, what we first want to do, okay, and what I suggest we first do is draw the parent chain first. Okay, so this is the name, penta-1,4-diene. So we can draw a zigzag consisting of 5 carbons, 1, 2, 3, 4, 4, and 5. Okay, so at positions 1, we have an alkene. At position 4, we have an alkene. Okay, so penta 1, 2, 3, 4, diene. At position 3, okay, there's something in position 3, we have prop 1 inyl. Okay, so we have 3 carbons, 1, 2, and 3, and at position 1 of that substituent, we have an alkyne. Okay, so and if we draw it cleaned up, it would look like this. So let's draw that quickly. There we go. Okay, so let's confirm that. Okay, so here's the drawing, and it's the same. Okay, so it's the same. Okay, So let's go to the next structure. Okay, so we have a cyclic compound with two alkenes and a linear part of that compound with an alkyne. Now remember, we have to choose the we have to choose the highest priority given to more unsaturated points. So there should be more alkenes in our parent chain. So we have two alkenes here. Okay. And this will be our parent chain. So if we count the number of carbons, 5 carbons, cyclo, penta, and then we have two alkenes, diene. Okay, so we have at the positions 1, 2, 3, 4, and 5. Is this the most optimized? Okay, yeah, 1, 2, and then 3, and then 4, and then 5. However, if I'm not mistaken, we cannot do that because we have to imagine that the substituent, okay, which is our ethenyl, okay, this is our ethenyl. We have the two carbons, or ethynyl. Okay, this ethynyl is just a substituent, so we shouldn't prioritize it when building our systematic parent name. So when we do the numbering 1, 2, 3, so we give the smallest numbers to our alkenes, 4 and then 5. Okay, so when we form that cyclopenta 1, 3, diene. Okay, since that's the end of our word, we end it with diene. Okay, and then at position 5 we have our ethynyl. So 5 ethynyl, cyclopenta 1, 3 diene. Okay, so that's correct. 5 ethynyl, cyclopenta 1, 3 diene. Okay, so for our last discussion on the first part of organic nomenclature, we will be dealing with aromatic carbons. Okay, so later in the course, you will determine that aromatic compounds satisfy 4 criteria. They are cyclic, all their atoms contain p orbitals that overlap each other. They are planar, they have sp2 carbons, and they have a set number of pi electrons, which they term as the Huckel rule. Okay, so aromatic carbons come in different shapes and many sizes. However, we'll only be dealing with 2 primary aromatic carbons, which is benzene and naphthalene. So benzenes are named much like cycloalkanes. Okay, we first determined the priority functional group, which is benzene. Okay, so always remember that if you see a benzene ring, automatically name it as benzene. Do not try to use the cyclohexa alkene because it would be named incorrectly. Okay, so when you see the structure of benzene, you name it as benzene. Okay, So that's our parent chain. Then we identify the substituents. We have two ethyl groups and a methyl group. And then we proceed to locant numbering. Okay, so this direction is optimized to give us the lowest numbers for each substituent. So here we go. We have 1,2-diethyl 4-methyl benzene. Okay, since we have two ethyl groups. Likewise, when numbering benzene, we do not consider the positions of the alkenes in the benzene ring. Okay, you'll later find out that it's because these the positions of these double bonds actually switch. No, so the basis for numbering is a substituent in this case. Okay. Okay. So benzene substituents, however, when they are connected to a parent chain, we use the word phenyl. Okay, phenyl. Okay, so in this case, the position 1 of a phenyl group is always the carbon connected directly to the parent chain. So that's 1, 2, and then 3. In this case, we have a methyl group connected to the phenyl group. So the complex substituent in this case will be termed 3-methyl-phenyl. Okay, so for substituents, we use the phenyl suffix. Okay. So there are also IUPAC recognized aromatic substituents. This is benzyl. Okay, so it's phenyl methyl, and it can only be used without substitution. So the difference between phenyl and benzyl is that phenyl has the sp2 carbon directly connected to the parent chain, but in benzyl we have a CH2 group or a carbon group bridging the parent chain and the benzene ring. Okay. Here are some IUPAC recognized substituted benzenes. Here we have toluene and styrene. Both are common additives for example, glue. Toluene, for example, the active ingredient in rugby, and styrene, the precursor to polystyrene, which forms our styrofoam and styrocups. So toluene in the proper systematic name is methylbenzene, while for styrene it's vinylbenzene or ethanylbenzene. Okay. So here are some other recognized disubstituted benzene. So they have two substituents. We have xylene, which is two methyl groups connected to a benzene. Okay, so depending on their position, they can be termed 1,2-xylene, 1,3-xylene, and 1,4-xylene. They also have another name, which is O-xylene, M-xylene, and P-xylene, which I will explain right now. Okay, so why did they use O, M, and P? O, M, and P come from the positions ortho, para, and meta. Okay, so ortho, para, and meta are indicators of location relative to a substituent. So for example, we have a methyl substituent here. Okay, if you want to refer to what is ortho to this substituent, you will look at the positions that are directly adjacent to it. Okay, so this is the ortho position. Okay, if you want to refer to the meta, this is the position that is 2 carbons, okay, 2 carbons away from the reference point or our substituent. And para is the position that is directly opposite of our reference point. So when we say orthoxylene, in this case, we mean that from a reference point of this methyl group, they are one carbon apart only. Okay? So that's orthosilene. And if we go back, we can see that for orthosilene, one carbon away. For M-silene or metasilene, 2 carbons away. P-parasilene, directly opposite or 3 carbons away. So this works. This is usually only applied for benzene. Okay. Okay. Now we move on to naphthalenes. Okay. So they are shaped like so. They look like two benzene rings connected to each other. And they are named like cycloalkanes. Okay. So they're not named like bicyclic compounds, even though they are bicyclic. They are named like cycloalkanes, and so we term the priority functional group naphthalene in this case. So when you recognize this ring, make sure that it always contains the 5 double bonds and 2 10 carbon rings. Okay, this is a total of 10 carbons ring system. And then you name it naphthalene. Okay. So next, we identify the substituents. We have methyl here. Okay. And then we begin locant numbering. Now, it has a special locant numbering. Okay. We always have to start numbering the locants adjacent to a bridgehead. So here is our bridgehead. Remember, from bicyclic compounds, we always have to start number 1 adjacent. So we can start number 1 here, number 1 here, or here, or here. Okay? And we always have to go in a certain direction from away from the bridgehead. So once we start from the bridgehead here, we have to continue number 2 here. 3, 4, 5, 5, 6, and 7. Notice also that I went directly 5 here. Okay, remember that it always skips the bridgeheads. Okay, because technically we cannot substitute anything on these 2 bridgehead positions. So the numbering always skips. Okay, so I'll just erase this. So we start number 1 there because this is the closest to our substituent. Okay, so we start. There's our bridgehead 1, 2, 3, 4, 5, 6, 7, and 8. Okay. So when you assemble 1-methyl naphthalene. Okay. In common naming, much like in benzene, we have the ortho, para, and meta positions. In naphthalene, we have what we call the alpha and beta positions. The alpha positions, notice they are closer to the bridgehead. Okay, so they are the positions 1 carbon away from the bridgehead. While the beta position is are the positions 2 carbons away from the bridgehead. And so here in this case, our 1-methyl naphthalene can also be called in common name alpha-methyl naphthalene. While this carbon, which is in systematic name is 2-methyl naphthalene, is termed beta-methyl naphthalene. Okay, so just remember alpha and beta positions. Okay, so let's try these simple exercises. Okay, so recognize that we have 3 bonds within a 6-membered ring. They are not directly connected to each other, and so this is what we call our benzene ring. And we use the parent name benzene. Okay. Next, we identify the carbon atoms or the substituents here. So we have a propyl group, And so the name is propyl benzene. Propyl benzene. Okay. Number 2. Okay. We have our benzene ring. Okay. Benzene. At the substituent, we have an ethyl group here connected directly to the benzene parent chain. Ethyl, and at position 1 of that ethyl group, we have a methyl group. So we have one methyl ethyl, benzene. You can also name this as isopropyl. Okay, so 1-methyl ethyl benzene or isopropyl benzene. Okay? Okay. I think this is a correction. We have to write parentheses here. Okay, number 3. Okay, we have our benzene ring, easily recognizable. Benzene. And then we have our substituent, which is a cyclopropyl. Okay. And so we have a cyclopropyl benzene. Okay, cyclopropyl benzene. Okay. And here we have benzene again. Okay, and we have two substituents this time. We have ethyl and methyl. Now, how do we choose the numbering in this case? Well, we cannot use the double bonds because it's a rule for benzene. We cannot use double bonds as a basis. We cannot start. We have only 2, so we can choose any direction really. But remember, on our very first naming exercises, we have to choose, in this extreme case, we have to choose based on alphabetization of the substituent. So we have E versus M. Okay, E comes before M in the alphabet, so 1, 2, and then 3. Okay, so we have 1 ethyl, 3 methyl benzene. Okay, so 1 ethyl, 3 methyl benzene. Okay, let's go to the next example. Oh. Okay. We have benzene. We have a methyl group here. And we have here a ethenyl group. Okay, I have an ethenyl group there. Now when we number, we base it on alphabetization again. So 1, 2, 3, and then 4. Okay, so when we write 1 ethenyl, 4 methyl benzene. Okay, so again, 1 ethenyl, 4 methyl benzene. If you chose to use vinyl, you'd have to switch the numbers around because alphabetization. So if you used vinyl, 1 methyl, 4 vinyl benzene. Okay. Okay. And let's go to this one. Okay, this is actually moderate, but I do want to try emphasizing this. we have a bicyclic compound and a benzene ring. Now, take a guess. Which do you think should be our priority functional group? Okay. Well, in this case, no, the priority would be our bicyclic ring. Okay, and I'll show you the hierarchy of that after we solve this. Okay, so we first name this as our parent chain. We have 1, 2, 3, 4, 5, 6, 7, 8. So this is oct, bicyclo-oct. Okay, and then ane, because it is an alkane. And so we determine this middle bit, which we have the square brackets for. We have 2 carbons in this direction, 1, 2, 2 carbons in this direction as well, 2 and 2. So 2.2.2. Okay, and then we start numbering. Okay, or well, we first determine the substituent first. Okay, so this is the substituent. Have a benzene ring here. And what's the substituent name for our benzene ring? Well, it's phenyl. Okay, so at position, okay, bridgehead will always be 1, and then this will be 2. Okay, so at the 2 position, we have a phenyl group. We have bicyclo, oct, square brackets 2, 2, 2, ane. Okay, so 2-phenyl bicyclo 2,2,2-octane. Okay, I forgot something. The bicyclo comes, the octane comes after the numbering. Okay. Apologies for that. There we go. So bicyclo 2,2,2-octane. And so when we choose the parent chain, we have to remember that monocyclic goes is the lowest priority, followed by monocyclic aromatic. Okay, so this goes for benzene rings, naphthalene rings, and then followed by your highest priority, which is bicyclic. Okay, so that's the hierarchy. So in summary, we discussed alkanes, we discussed cycloalkanes and bicycloalkanes and how to name them, with alkenes and alkynes, and the case between if we have an alkene and alkyne in the same compound, Enynes, and our aromatic carbons. Okay, and so the general flow of forming a name is that we first determine the parent functional group, okay, whether it has an alkene or an alkyne, find the parent chain, okay, so the longest number of carbons, or the other choices in particular, or if they have more alkenes or alkynes in that chain. Identify the substituents first, and then begin locant numbering and considering all the factors, including the number of alkenes and alkynes, the parent functional group, and the substituents. And lastly, we assemble the name with some particular grammar points. Okay.